All right. Good afternoon, everyone. Thanks for coming. This is the lecture 12 of our course on quantum computing. So as usual, let me start from the quick recap of what we discussed last time. So last lecture was lecture 11, and we discussed like general requirements for the quantum computers. And we discussed the elements of photonic quantum computers. Let me go through just very quick. So for the requirements that we impose on a quantum computer, we have a list of 5. Essentially, all this means simply that we need a good, reliable qubit that we can scale, right, to a system of a number of quantum qubits that we can couple to each other in a controlled way. The qubits that we can address and initiate in a particular state of our interest, and that we can read out after the quantum algorithm executed. Right. So we said that today's quantum computers, they are mostly based on superconducting qubits, with some exceptions of photonic and atoms and ion-based quantum computers. I would say the vast majority of today's quantum computers are superconducting, and this is the subject of our today's interest, this superconducting quantum computers. Yeah, in terms of photonic quantum computers, we said that we can encode the information, the quantum state, in different degrees of freedom. The simplest way to encode quantum information is the propagation direction, like light propagating to one direction, like horizontally can be one state, light propagating upward, vertically it's another state, and we can already use this encoding into the direction of propagation as the simplest quantum bit or qubit. Another approach, yeah, and this encoding into the propagation direction is widely used by the devices like the interferometers that we use for sensing and many other applications. Okay. Another degree of freedom that we use to encode the information is the light polarization. We know that the light in free space is a wave with a polarization plane, right? So usually by this polarization plane, we name the plane in which electric field oscillates, and this plane, the polarization plane, can be vertical again or horizontal, and we can encode the quantum state in these two possibilities of vertical and horizontal direction of the light polarization. We can play with the polarization. We can select a particular polarization with a device called polarizer. In other words, this polarizer works as a device that detects the polarization state, right? And another polarizer, which is called analyzer, we can control the amount of polarized field that passes through the entire device. Anyway, so we can play around with this polarization, we can convert polarization, and we can build linear optical computing, linear quantum optical computing based on the mm, control of the polarization state or propagation direction state. So in this sense, optical quantum computing is great in terms of well, light propagates at the speed of light, right? The fastest speed in nature, and light also don't interact with the photons, the elementary particles of light don't interact with each other, so the light just passes through without interaction, which is, by the way, a very interesting phenomenon, right? This fermionic state don't interact, but form the interference pattern. Okay, so the photons don't interact, but if the photons coherent, they form interference pattern. And if you superimpose two beams of photons of electromagnetic field, the one beam affects the other beam, but that's not the photon-photon interaction. I suggest that you think about this a little bit because that's pretty interesting phenomenon. What happens when light interferes with each other or with another beam of light at the elementary particle level? Anyways, even though we have a number of designs for 2-qubit optical gates, which is based on optical nonlinearity, due to the fact that this optical nonlinearity is intrinsically weak, it's very hard to create a scalable 2-qubit, 3-qubit gates. That's why this photonics, optical quantum computing, is not that popular. People work in this area, and especially the area of exciton polaritons, when we couple light to other states of matter, is a great phenomenon and develops very extensively. In my lab, we do several projects on that. Yet, this is not the mostly used approach for quantum computing today, let's say this way. Maybe in 10 years or so, it won't be the case. All right, in optics, we can even entangle photons using the effect of spontaneous parametric down conversion. And this was the first experiment to create entanglement, quantum entanglement. And in fact, until recently, this was the most popular way we entangle photons and then use them. That's crucial for quantum communications, for quantum cryptography, for quantum key security key distributions, and so on. For some protocols, okay, so some protocols of security key distribution doesn't require the entanglement. Anyway, so people work in this area a lot, and as a state of the art, I demonstrate you this this photonic quantum computer that has been published, reported very recently, a few years ago, by this Chinese group, and the computer is called this Jishang, whatever. So the system, so the main point about this, the main fact about this system is that it is linear computing. So it doesn't require this protocol, this quantum the approach doesn't require 2-qubit gate, so it's a linear optical computing. And today, all these trend is to scale down everything to a chip size, to chip scale, and operate with optical pulses, conduct optical computing, and the chip scale device. Also, a system like this is very useful for optical artificial intelligence when these interferometers, as just we discussed last time, interferometers are used as these artificial neurons. Yeah, so people design these integrated photonic chips. Intel does in this area a lot. Yeah. And another trend is to even push everything down to nanometer scale, because at the nanometer scale, the light interacts with matter particularly strong, provided that you squeeze light. So one great feature of light is the fact that you can squeeze it. Like you take light, like photon, you can squeeze it. So you can reduce the size of a photon. The size of a photon is, as you know, about the wavelengths of light, which is about 500 nanometers. And designing a so-called antenna or nano-antenna, optical antenna, you can squeeze the size of a photon to a few nanometer size. And this squeezed light or localized light strongly interacts with matter. And this is essentially what leads to this excitonic response. Very important, very popular subject today. Yeah, so this is what we discussed last time. Let me transit to today's lecture, unless you have any questions. So today we're going to talk about superconducting qubits. Initial plan was also to discuss the neutral atom type of qubits and quantum computing, because that's also a very actively developing area today. But later today I realized that I better to focus on one type of computing, because to avoid this mixing of the subjects. Okay, so in the literature, more to read, I provide some references specifically about the other types of qubits. And we also will discuss the conclusions. I will give you some information about where, for example, if you're interested in the subject, where you should go to search for the quantum jobs, opportunities, and so on. All right, so do you guys see my slides well and hear me well? Anyone? Oh, okay, in the chat, yes. Okay, thank you. Alrighty, yeah, so as usual, I refer to the previous course lecture, right, in the recorded format, for more details, but essentially this lecture is updated version of the previous one, because this is the final concluding lecture. So yeah, just to refresh, right, the why we need a quantum computer, what's so important about quantum computer. The main purpose of quantum computing is that with a quantum computer we can solve fundamentally different class of problems that is solved by classical computer. Okay, sometimes if you watch these lectures on quantum computing or other types of computing, people start with this Moore's law, stating that, oh, we cannot grow the number of transistors any longer. That's not really the case, because we can always parallel different processors. And even though the number of transistors cannot grow per inch, right, cannot grow forever, we can grow in terms of number of CPU. It doesn't really, is not a problem. What is a problem is that classical computers cannot solve a particular class of mathematical problems, and this class of problems is pretty large, as we know. For example, today, so if you look at this periodic table of chemical elements, right, you will see like over 100 different elements there. And guess how many simplest chemical elements we can simulate today using the classical computer? Just a few. Hydrogen, helium, and maybe some other simplest elements. The vast majority of the table cannot be solved using classical computer, because the complexity of each of this problem grows with the number of nuclei, with the number of protons and neutrons in the nuclei, and number of electrons too. That's very difficult and not tackable task by the classical computer. Quantum computer uses completely different approach. It can solve such a problem. So classical computing solves polynomial class of problems. Quantum computer solves non-polynomial class of problem. At the same time, like if you wonder, like, can we solve using quantum computer? Can we solve polynomial complexity class problems? The answer is not really. Like if the quantum computer is not the computer to compute things like 2 plus 2 or something like that, like to multiply numbers. So it's different. Okay, so quantum computer will never replace classical computer. It is a different machine for a different purpose. Okay. For the classical problems, for the polynomial class of problems, the people develop other types of computers, like photonic computer, when we try to replace the electrons with photons and develop these optical photonic processors, transistors, and so on. Yeah, but that's like improvement, advancement of the conventional electronic computing. Alrighty, yeah. So this is about the purpose and how we actually realize that. To realize the quantum computing, we need 3 ingredients, right? The first ingredient is a quantum superposition. Again, if a quantum system can exist in different states, we have to take into account that the system exists in all of them. Is this a feature of the size of a system? Apparently, that's the answer is no. So typically a small particle, why it exists in the quantum state, in what we say unusual quantum state, simply because the electron can be isolated, so it doesn't interact with the rest of the world. So it keeps this quantum state naturally. And it turns out that provided that we can isolate the classical, like a big system, like a micro scale system, if you can isolate yourself from the rest of the world, you can be in the quantum state. That's the something that people realized relatively recently. And the quantum state, the fact that we today, that we have these superconducting quantum computers is the realization, is this the realization of this fact, because the quantum circuits that we're going to discuss today, they are macroscopic. Okay, so you can actually see them. They are not small, so you can realize quantum effects in large objects. Okay, so the quantum superposition, we need that. It's easier to achieve for small particles, much more difficult to achieve for large particles. But if a particle or a system is isolated from the rest of the world, it will be found in the quantum state, in the superposition of all possible states. And of course, if you measure the system, the quantum state of the system collapses to one particular state, right? So usually, like for quantum especially, we don't need many, we just need two. And the system with two quantum state is called qubit. The Christomatic way to create such a superposition of two states is just to make a screen with two slits like this. By making slits, we truncate all the possible states to just two, right? One that for the particle that passed through the upper slit or through the lower slit, just two opportunities. And as we just discussed last time, for these two states, we can use the direction of the photon or polarization of a photon and use this photonic quantum computing. Other approaches include the electron spin that can be polarized up and or down. And when we detect spin, it is always either up or down and nothing in between. And the atoms, of course, atoms at the atom transitions, if you manage to isolate atom with two energy states selected from other energy states, you can use these energy states for your qubit, right? The second key component of any quantum computer is a quantum entanglement. Again, if you have isolated systems, isolated qubits, the general, the total quantum state is the tensor product of the states of each qubit, right? And with the difference comparing to the system with interaction, so by this red spot here, I indicate interaction between the two. So when you get interaction, you get these coefficients C00, C01, and so on, that are not related to the initial ones. Okay, so these amplitudes now depend on the state of both qubits, and the system becomes entangled. If we scale up the system to 3 qubits, now the number of these coefficients is 8, which is 2 to the power of 3. And if we continue this scaling further, the number of basis states of our computation system grows exponentially, 2 to the power of n. And if the system gets like 50 qubits, this number is already very large, colossal. So just 50 qubits creates this huge number of basic computational states. Okay, so in input we have 50 integers, 50 zeros or ones. In the output, of course, we also have 50, but between this initiation and measurement, we get a colossal, a huge number of basic of computational basis states. And that's what we call quantum parallelism, because we can compute all these states like simultaneously at the same time. Okay. Yeah, this is what we call quantum parallelism. The key component of any quantum computer is a quantum interference. Why? Because, as I said, we have n in input, n in output, and a huge number 2 to the power of n in between. And we need to somehow arrange the superposition of the states so they constructively interfere and lead to the answer, that is to the correct answer, the answer we are after. Right, and this is achieved through so-called quantum algorithms. There are many different algorithms. In our course, we discuss some of them. Okay, like Grover search algorithm or Deutsch algorithm or Fourier transform, quantum Fourier transform algorithm, and so on. Okay, so there are many types of quantum bits or qubits, and many platforms for quantum computing that people develop today. As I said, there is no like one approach that like works perfectly. Every system has pros and cons, advantages and disadvantages. And that's why many companies and many labs develop different. So here for this slide, I found this table here on this web page. We found this table with the main qubits, right? Starting from like atoms. This technology is very popular today. Cold atoms, the quantum annealing, which is rather the approach, the superconducting qubits that we discussed today, the quantum dot approach, like silicon quantum dots, and the centers, which we also study in my lab, topological and photonics, the last one. And here in this table, you can see for the vendors, different vendors and different labs. And yeah, you can acknowledge how many groups and vendors, companies work in this quantum area. You can also notice the difference between vendors and labs. The vendors, if you see, typically, like if the company is IBM, right? The IBM develops mainly one particular type of quantum computers. For example, these superconducting quantum computers. You cannot see IBM in any other. So the companies, vendors, they kind of focus on a subject and develop the subject, particular one. In drastic contrast to labs. So labs like MIT, the universities, they explore broadly. And I would say this is a main difference between academia and industry. In academia, we investigate broadly the things, we explore. and not really tied to one subject. Industry, of course, tries to make revenue from from the particular particular type of computing in this case. Anyway, so yeah, I encourage you to look at this slide more to see if you like any of these companies. Maybe some of this will be your job place soon. Alrighty. Here I put this table of the state-of-the-art quantum computers today. And last time we discussed photonics, because I believe photonics is very easy to grasp what's going on there. It's as simple as a photon going to the left or to the up, right? And so simple. That's why I usually prefer to start from photonics. But today we're going to discuss superconducting, which is much more popular today and has much more importance for today's field. Few words about microwaves and quantum computing. So the microwaves are the part of the electromagnetic radiation spectra, right? So for example, here you can see different areas of the spectra, including, for example, radio frequencies, infrared, visible. This visible part is the part we actually see, right? Our eyes equipped with sort of detectors, photon detectors or antennas, if you wish, so we can detect light that comes to our eye. One can ask, for example, why we don't see in infrared, right? The answer is that at the room temperature, the infrared signal is too noisy. Like if we would be able to see infrared signal, our vision would be very noisy. The picture would be very, very noisy. Why we don't use ultraviolet for vision? Because ultraviolet is ionizing, right? Ultraviolet we use for this, for example, for computer tomography, in medicine. It's a ionizing type of radiation. Microwaves goes next. So typically the frequency of microwaves ranges somewhere around 10 gigahertz, technically from 1 gigahertz up to somewhat about 100 gigahertz. And we use microwaves for communications, right? This Wi-Fi, internet, 3G, 4G, 5G, 6G is all about microwaves. Well, 6G is maybe already comes to the millimeter wave, but the vast majority of this Wi-Fi communication type is microwaves. And microwaves are very developed. After the Second World War, when the army used microwaves for radar technology, right, for communications, microwaves developed and has been developing has been developed in a very very extremely useful area of technique, right? Today we can very nicely, very finely, very precisely generate any type of microwave signals. We can guide the generated signals through different waveguides. We can trap the microwave energy in resonators of different kind resonators. We can receive and emit microwave waves using antennas, and so on. So we can convert the frequencies. So this area of electrical engineering probably one of the most developed today. Probably one of the most developed today. Maybe only electronics, right? This CMOS electronics can compete to microwave in terms of readiness, in terms of the state of the state of of the technology. So it's very desired to use microwaves for quantum. Okay. One can ask, why not electronics like transistors and CMOS electronics that we use for conventional classical computers? The answer is that so first of all, we can use, actually there is some types of qubits based on CMOS technology, but typically this type of quantum computing based on electronics is very noisy, like extremely noisy. So such a semiconductor qubit keeps the quantum state for a very short time. Okay, so there is a direction in this area where people develop fast electronics for initiation and readout. So people say, okay, it loses the quantum state fastly, but we can speed up our electronics, like readout, initiation, gates, to still conduct some quantum computations. And this is another very actively developing area today. But if talking about microwave, in microwave, we can first consider a resonator. So in this case, it's a planar resonator. Basically, so what you see here is a slab, like a chip surface, with made like a gold microstrip in this shape, right? So essentially, this is a number of straight metallic strips with a central part with a gap. So this central part with the gap works as a capacitor. It stores the charges, right, for some period of time, and creates the electric field in this gap. In the next time instant, half of the period, these charges form the current that goes along these straight parts, and this current creates the strong magnetic field. Okay, and these parts of the resonator work as an inductor. So it's a coupled system of capacitor and inductor that can intrinsically resonate at some frequency. Okay, so and we can design the circuits, the resonators, with the frequency of interest, like very precisely. In the picture in the center just demonstrates the mechanical analog of this. So in the electromagnetic resonator, we have the exchange of electric field to magnetic field and back, and vice versa. In mechanical resonator, we have exchange of potential energy into kinetic energy and vice versa. So essentially, if you understand the physics of the harmonic oscillator, that's basically what you need to understand to grasp the large part of all this physics. So quantum physics, quantum field, quantum field theory, and quantum computing as well very much based on this simple mechanical analog, the concept of a pendulum, okay, or the oscillator. And if you quantize the energy of the oscillator, just like the one like this, the planar resonator, the solution will be quadratic like this for the energy, and you will find the solutions of these energy states. Okay, so what it means basically is so let's suppose your energy. So let's suppose your system gets the total energy E0. Okay, so then your system like oscillates back and forth like this between the up to this total energy E0. If you add more energy to your system, it oscillates between these two points like this. So it's indeed works as a pendulum, as a harmonic oscillator. In quantum, what we have first we have empty resonator, meaning like no excitation there, and then we can add one excitation to our resonator, and the system transits from the smallest energy state, which is E0, to the first excited energy state, E1, by absorbing this, not absorbing, but capturing this h bar omega, and which is the energy of the excitation. Okay, and if you continue this, we can add one more photon, one more, and so on, so on. So by this we can go up and upper and upper by this ladder of energy states. But this cannot be used as a qubit, because here we cannot control particular transitions. Okay, like putting 10 photons to the system, we will get our system to the level 10, which is not what we need. We need to isolate our system, our transition between, for example, these two, E0, E1, and work here rather than going up. So how we can turn this system into a qubit? One approach, yes, and I just forgot to mention that this system typically is lossy. Okay, any friction, any dissipation leads to noise, and noise is very harmful to quantum. So we need to get rid of noise. And the way we get rid of noise in a resonator like this, we can just cool down the circuit, right? Our circuit is made of metallic wires, and if we are aware of this superconductivity effect, for some metals, for example, aluminum or plumbum, niobium, if we cool these metals down below critical temperature, the critical temperature is different for different materials. For aluminum, it's around 1.2 under the common pressure. Okay, plumbum becomes superconductor is around 7.2. Niobium, a very popular material for this, is about 9 Kelvin, and so on. Today we have like materials with much higher critical temperature, and typically those materials are alloys of different metals and ceramics, and like if you ever saw, for example, these MRI machines in medical clinics, right? This MRI, this magnet, it gets a superconducting coil in there, and these coils are made of particular metal alloy that turns this magnet into a superconducting state that creates very strong current, and strong current means very strong magnetic field. Anyway, so one effect that associated with the superconductivity is the transition from conducting state to the superconducting state, basically when the resistance vanishes. Vanishes means becomes undetectable. Like this effect has been was observed by Kamerlingh Onnes, and this group has been like the only group who could create liquid helium for these experiments, and they were monopolists, right? They didn't have any competitors in this field. And what they done, they created a loop of hydrogen wire. This is, oh, sorry, mercury wire, sorry, and created the current there through the electromagnetic induction effect. And then they measured this current after several years, and the current was there. So it means that in this loop, the current didn't like decay after several years. So it looks like the material is indeed like zero dissipation, zero loss. Another effect, which is associated with the superconductivity effect, is so-called the Meissner effect. So the Meissner effect consists in the fact that in superconducting state, the superconductor, the material, repulses the magnetic field from its bulk to the external area like this. So it doesn't allow magnetic field to get inside of this material, which is very interesting because, as we know, magnetic field is very hard to screen, right? The electric field is easy to screen. You just make this Faraday cage, and that works perfect. Like Faraday cage, if you heat your food in the microwave, you know this grid, right, on at the wall of at the front wall of your microwave. So that's exactly Faraday cage. It doesn't allow electric field to go out from the microwave, and microwave is safety. The magnetic field doesn't work like that. Magnetic field is very hard to screen, and only below this critical temperature, due to the Meissner effect, magnetic field can be screened. Yeah, so we use superconductivity effect to make our circuits more low loss, like lossless or loss efficient. And that can be done in two different ways. So to do so, we use the cryostats, right? Cryostats of different type. So on the picture on the left, we see a typical closed cycle cryostat. This is exactly the one we have here at FIU in my lab. So this closed cycle cryostat provides us the temperatures as low as 3 Kelvin. So we can cool down the materials to 3 Kelvin temperatures and then investigate them through different approaches. And from this table, you can see that below 3 Kelvin, we have, for example, all these materials are in superconducting state, even indium too. So all these materials are superconducting using this approach. However, for quantum computing, specifically for superconducting quantum computing, it's not sufficient to just reach the superconductivity effect for many reasons. And the main one is that in the superconductivity effect, so let me say this way. So the dissipation, the resistance is zero in the DC state. So when you have direct current, no oscillations, the frequency is zero, then dissipation is zero. However, if the frequency grows, this residual level amount of dissipation appears because of the oscillations. And this loss leads to dissipation, to noise. So we need to cool our qubits, superconducting qubits, even below 3 Kelvin, actually much more, well below 3 Kelvin. And today's quantum computers, they use so-called dilution refrigerator. So this dilution refrigerator is a piece of art. So even for cooling systems below 3 Kelvin, they use the quantum effects. They use the dilution of different how it's called, the helium, different versions of helium. Okay, so they already use quantum effects even to cool down the samples below 1 Kelvin. And typical quantum computers today work around 10 millikelvin, which is almost zero, right? Almost zero temperature. At the same time, the system is much larger, much bigger, and much more pricier. So yes, only giant companies like IBM or like big national labs can afford something like this. Alrighty, yeah, so we cool down the circuits below 3 Kelvin to make them superconducting. That's not sufficient to make quantum. We cool them down to 10 millikelvin to get rid of the noise, and that also not sufficient to make them quantum. What actually makes them quantum is the use of nonlinearity. Okay, if you return to go back to this slide here, the transition, right? We say that we need to isolate just two transitions, for example, from 0 to first excited state. How we do so? We can achieve this isolation of two states from others if the excitation that we have between these two states affect the other states. So as soon as there is the resonator like this captures one photon, the field of the photon changes, like affects the frequency states of all above states. Okay, so like frequency, for example, becomes smaller, and because of that we get this mismatch, energy mismatching, and the circuit cannot absorb another photon like that because of this energy mismatch. And to do so, we use the effect, which is called Josephson junction effect. The Josephson junction is the composition, is a junction of two superconductors. Okay, so long story short, the superconductivity is because of the formation of so-called Cooper pairs. So the electrons, they are fermions, right? Spin 1/2. They intrinsically lossy. They interact with the crystalline structure and so on. However, below critical temperature, some materials can form Cooper pairs. And this Cooper pairs is just a pair of two electrons. And a pair of two electrons is a boson. is a bosonic particle. The electrons becomes bosons. And bosons just like photons of light. So the light can travel through pieces of the electric, just like through window, right? We have window. Window is an isolator, but light passes through the window and we can see through the window. So something happens, something like that happens here. We have two superconductors with Cooper pairs. The superconductors are isolated with a piece of isolator, which is not penetratable, right, to electrons, but Cooper pairs can tunnel through this isolator. And this process turns out to be very nonlinear. Like if you make a device like this, and if you excite this device with just one electron, then this excitation affects these processes very much. So in terms of, in the language of formulas, we say that this device behaves as a nonlinear inductance. Okay, so this device works like a wire coil with inductance, but in contrast to wire coil, this device is very nonlinear. Is nonlinear at the level of single excitation. So we put this Josephson junction into our circuit. Okay, as I said, it behaves as an inductor, so we can even solder out the inductor and use the Josephson junction instead. Okay, so this is the conventional LC resonator, and with the energy spectrum, as we said, it's an equidistant energy ladder. If we put the Josephson junction instead of inductance, we get this nonlinearity. So instead of parabolic energy spectrum, we get sinusoidal energy spectrum. And this sinusoidal energy spectrum leads to non-equidistant energy levels. And we can now isolate the state 0 and 1. So we can work in this spectrum. So physically, it means that the resonator like this captures only one excitation and then cannot capture other, cannot trap other excitations because these levels are detuned from the fundamental one. And on this picture, we can see this scanning electron microscopy image of this Josephson junction. So we see here two metallic parts made of aluminum. So you see aluminum typically, I mean, aluminum is not a good metal. It always form these defects and like areas, defects on the surface. We call them domains, right? They form domains, so it's granule. But funny fact about superconductors is that typically bad conductors at room temperature became superconductors below critical temperature. And in contrast to good conductors like copper or gold, these materials don't have superconducting state. That's very interesting phenomenon. Anyway, so aluminum structure like this, and these two metallic parts, they are separated by a very thin layer of dielectric. In this case, that's like sapphire, this dioxide, aluminum dioxide, sapphire material. Yeah, so this is how it works for This is what is a Jefferson junction-based qubit. We add Jefferson junction in a resonator. This resonator, by the way, can be of any type. It can be bulk resonator, it can be cavity, like metallic cavity, it can be whatever. If you take a metallic can that can store energy at the particular frequency of interest, and if you add a device like this inside of your can, like coffee can, you know, it will be a qubit. Bad with bad characteristics and so on, but it will be a qubit. Provided that you cool down the system below, well below 1 Kelvin. Do you have any questions so far while I'm drinking some water? All right. So how we control such a qubit? Well, let's consider the two states, 0 and 1, just like these two, we isolated from the rest of the other states. Okay, so for the moment we forget about all the states, provided that we work at the frequency that matches this omega 0, 1 frequency transition. If we send a pulse to the system, usually the system exists in the ground state. It decays to the ground state. Okay, so if we take the system that didn't interact with any pulse before, we will most likely find the system in this 0 state. Then we send a pulse with some duration tau. Okay, and it turns out that if we set this tau to be, I mean, to a right amount, okay, we can excite this system to the state 1, to the excited state. This is pretty much how it works on this panel on the right. This is pretty much what happens. Like the red is the state 1 probability, the blue is the state 0 probability. So at the initial time instant, we have system in the ground state with 0 probability in the state 1. And then let's say I'm sending a pulse with tau equal to 0.5, which is here. Okay, 0.5. In terms of 2p over omega, which is just normalization factor, this is a very important parameter in quantum. It's called Rabi frequency or Rabi energy. It's not very important for us for the moment. Right, so we have this tau parameter. We design this parameter to 0.5, and I'm sending the pulse with this duration. What happens after the pulse passed through the atom? It leaves the atom completely in the excited state, in the state 1, with 0 probability of finding this atom in the state 0. So the atom transit to the excited state, and so on. And this is exactly what X qubit does. Right, the X qubit flips the 0 state to the state 1. And if I start from this state, in the excited state, if I send another pulse, just like the first one, I will transit to this state, to the state of the zero state excitation with zero probability in the state one. So I cannot only raise the energy of the qubit, I can transit it in the reverse way from state one to state zero by sending just another pulse. So I can flip this qubit from 0 to 1 and from 1 to 0. So this is exactly X gate. Let us now look at this point here. So this is exactly the point of probability amplitude 0.5, where the probability of finding the qubit in the 0 state and the state 1 is exactly the same. And this is the state of, this is the state plus, right? This is the perfect balance superposition of two states, just like what we discussed many times throughout this course. So what it is the Hadamard gate. So I came conclusion to the fact that if I take tau of 0.25 somewhere here, I will reach the state plus, and my new pulse is the Hadamard gate. So you see that for this platform, for the superconducting quantum computing, the gate is just a pulse of a tailored design duration. I change the duration of the pulse, and it behaves and it makes different gates. Okay, so that's why it is very nice, because I can do computation by sending pulses without the need to like create a large circuit, connect all these things. If my gate is just a pulse, I can design the pulse and work with it. That's very, very useful. As I said in the beginning, today we can design microwave pulses like extremely precisely. In fact, yeah, microwave facility is one of the most precise facility existing today. We have these quantum clocks that we use to measure time. Many examples, gyroscopes, and so on, based on microwave effects too. Let us consider now the simplest single qubit Josephson junction circuit. So JJ stands for Josephson junction. So here on the left, we can see the circuit of the real structure demonstrated on the right. I took this picture from the article, from a review article. I put the reference to the, in the reference list. Okay, so what we see on the picture on the right is the two Josephson junctions. If you zoom this area enough, we will see these two Josephson junctions here. The system of two Josephson junctions, traditionally it's called SQUID. The SQUID device, which is simply a coil. Like topologically, it's a coil with two Josephson junctions in there. Why we need coil? Because this coil can be tuned with the external magnetic field, but that's not important for now. What's important is that we can connect this device, this Josephson junctions, to a resonator, like here, this microwave resonator on the surface of a chip, and then we can couple this resonator to the rest of the circuit. For example, we can couple it to another resonator like this kind of meander meander line. This meander line works as a readout resonator, as a filter. We call this a parcel filter anyway. So it's a filter that we use to like read out, initiate and read out the qubit. So what is qubit here? Qubit is this blue cross and this very, very tiny area with the Josephson junctions. This is the qubit. The rest of the circuit is the excitation readout part and control, like Z control part, and so on. And the picture on the left demonstrates the RLC circuit of this. So this is my Josephson junction based qubit. Over here, I capacitively couple this junction, this qubit, to the readout filter, readout resonator, like shown here. And then through a circulator, I can excite and read out this qubit through in my circuit. So essentially, it is all about microwave engineering, electrical engineering. And today, all these companies, we will talk about this in the end of the lecture, but today we have a lot of companies, a lot of groups who need electrical engineers just like you with a good understanding of how microwave technology works, how to design these microwave circuits, and who have the knowledge and skills in quantum. Okay, this is very, very nice composition, like a person with microwave and quantum skills is highly desirable for the market, for the job market. Today, unfortunately, we have the shortcut of the workforce, right, in this area, and our department receive more and more requests for the students with the good understanding in quantum and microwave. So people who want to continue your career in this field, you are just in right place. Alrighty. Few words about decay and dephasing. Right, I said that microwave oscillating field unfortunately creates noise because of the residual resistance, but that's just one source. Another source is that you see these Cooper pairs, right? These Cooper pairs exist because they are coupled with some energy. And if the energy of microwave pulse exceeds the energy of coupling of the bonding of the Cooper pair, this microwave pulse destroys or can destroy the Cooper pairs. And destroyed Cooper pairs is simply two electrons. And electrons resist, right? It decays. It converts field into heat, into dissipation. So unfortunately, all these effects are not avoidable. That's the fact. And all these processes and a number of others, I don't have to discuss all of them, lead to two different effects: decay and dephasing. We discussed decay and dephasing at the lecture number 4, I believe. So I encourage you to read more about this. Long story short is that if we excite a qubit to the state 1, eventually it will decay to the state 0. This is what we call decay. simply the qubit just loses the energy. It can lose energy through radiation. It can lose the energy through dissipation and so on. And this process is characterized by this transition time T1. Okay, so if you recall, we went to IBM Quantum and they specify T1, T2. So this is exactly T1 from there. Dephasing. So let's say our system is sensitive to some parameter lambda. It can be, for example, microwave or magnetic field, okay, or temperature or something else. And let's say this parameter fluctuates. And this fluctuation will lead to fluctuation of the energy state. So the energy state is no longer just a defined line, right, in this graph. It's rather the area. And this spread leads to dephasing because different excitations will acquire different phase, and the phase will be destroyed. And this is a very harmful effect for quantum because dephasing leads to loss of quantum state of the quantum superposition and so on. This process is described by T2, or rather T2 with a star. Here in the literature you can find this T2 with a star. So this is dephasing time. Yeah, and these all processes are not available. They're always there. Okay, we discussed single qubit, how we initiate, how we read out, and what parameters describe a single qubit. How we create entanglement, how we create two qubit operations. In order to create two qubit operations, we need coupling. We need to be able to couple one resonator, one qubit to another qubit. And in microwaves, as well as electronics or radio waves, we have this approach of coupling through this coupling capacitor, right? When we have a key here, and when we need to couple the circuits, we just turn on this key, and the circuits will be coupled through the coupling capacitors. Something similar happens to the coupled qubits. So here in this picture, we have qubit 1, qubit 2, and they are coupled through a switch, but that's not mechanical switch. That's a switch that realized with the use another qubit. Okay, so this two qubit system gets another one, the third qubit, as a tunable coupler. Okay, so if you read like, this quantum computing contains 100 qubits. In fact, this is just 100 qubits like this one and two, but in parallel, we use a lot of tunable couplers, which also include these Johnson junctions with these qubits for coupling. And we can control this coupling through another port, providing just a sufficient amount of current or magnetic field. Yeah, so this is just a coupler that controls coupling of the resonators. Yeah, and this way we can achieve two qubit gates operations. We can achieve the entanglement and so on. So this is the summary, basically. Okay, so for the superconducting quantum circuits, we can use pulses for single qubit operations. If we use two pulses, we can achieve two qubit operations, like two qubit gates, like shown here. Yeah, without going into deep to this, just say that these single qubit, two qubit gates, just about the way we use the pulses. Okay, the pulses can be of different duration and different frequency. And yeah, so this is how we achieve 2-qubit operations, just using 2 different pulses of slightly different frequency. This slide demonstrates the result, right? We put together many qubits, make them able to couple in a controlled way, which is very difficult task. Like this transition from 1-qubit system or a system of single qubit gates to a system with entanglement is a huge technological technological step. And yeah, if you manage to do so, you can create something like this. So this is people say this is a quantum computer. In fact, this is not a quantum computer. This is just dilution refrigerator. This picture on the right. Right. What is the quantum computer? Is the small part in the very lower stage of this device. So here we see different sections, right? Like 1, 2, 3, 4, maybe 5 sections. This section is called stages, and different stages they have different minimum temperature that the stage can provide. So in order to go like deeper, like lower in terms of temperature, we need to put more stages, and of course there is a fundamental limit somewhere. Like my system in my lab, we have 2 stages, and the temperature we reach typically is the lowest one, is 3 Kelvin. So we are somewhere here. If one uses this state-of-the-art dilution refrigerator, you can reach 20 millikelvin or even 10 millikelvin and sub 10 millikelvin temperatures. One thing you can grasp from this picture is the fact that any quantum computer requires a lot of microwave facility, like generators, receivers, detectors, circulators, and so on. And everything is connected to the quantum computer with these coax cables and wires. And then the larger number of qubits, the larger this microwave facility part becomes. Okay, so for the applications, we need systems with let's say hundreds of thousands of qubits, and this quantum computer contains just 50 qubits. 1,000 qubits is much more wiring, much more coax cables, and so on. If you go to thousands, like 10,000, 100,000, this microwave facility becomes extremely large, and this is what we call the scalability bottleneck. We simply cannot put more and more qubits because of this microwave facility, because of these wires and so on. It makes the system very complex, very hard to manage, because for the proper operation you need to like connect the 2 points with in a precise way. So the scalability bottleneck is one of the challenges which to be solved by electrical engineers with quantum background like just you. The picture on the right shows the schematic of a simplest quantum computer. Okay, so we have this quantum chip with Josephson junctions, at the lowest stage of 20 millikelvin, we have input pulse sequences shown here in red. We have control pulse sequences shown here. And then we also have this readout pulse, readout part. This readout part is another technological challenge. The reason is that in contrast to initiation pulses, the input pulses that come from the room temperature and go to the chip, we can attenuate these pulses by a number of attenuators, like minus 30 dB, then minus 20 dB, minus another 20 dB. So the signal that comes to the chip is very, very weak. And that's how we can reduce the level of noise that comes from the room temperature. And this doesn't work for readout, because in readout we need to get as much signal as possible. So the use attenuators is not desirable. We actually need to get rid of any attenuators. But without attenuators, the room temperature from the noise from the room temperature goes to the quantum computer and simply destroy it. I mean, destroy the state, the quantum state. So people use a lot of stuff like circulators, parametric amplifiers, isolators, and so on, just to read out one qubit. But we need to read out maybe hundreds of thousands of qubits. So you can imagine how much, it must be scaled in terms of the number of these amplifiers, circulators, KX cables, and so on. It's a huge challenge. And this is another challenge that electrical engineers with quantum background can solve. Alrighty, so I'm coming to my conclusions. Advantages of superconducting qubits: scalability, controllability, readout, because readout happens through this microwave facility, it's pretty fast. Customizability, because we can design the circuit, the quantum circuit, like very precisely to the operation frequency and so on. We can design the pulses, and everything is compatible with classical electronics, classical microwave facility. Challenges, as we discussed, the decoherence, the need to cool down the circuit to extremely low temperatures, which makes the system very pricey. The scalability bottleneck, another problem. Another problem is the readout channel, when you need to use this pricey, lossy, and so on, the circulators, isolators, amplifiers. Crosstalk. As we put more and more qubits together, they start couple not only through the control coupler, but also through for example, through the free space, through radiation and so on. And this crosstalk and interference is another huge challenge in there. Another problem is that the larger the system, it's harder and harder to numerically simulate, numerically calculate the system, and so on. A lot of challenges. Some of these are particularly related to superconducting circuits. Some of them are rather broad and fair to other types of quantum computers and so on. Few words about advances right? We have challenges. That's why we need to develop, and this impose or motivates people to investigate alternative approaches. So this picture, this part is taken from our recent paper. So from main point from this paper, maybe, so here we demonstrate this road, like roadmap, starting from somewhere around 2000 year, like 25, 24 years ago, and up to today. So we already have the improvement in terms of T1, T2 at the order of 10 to the power of 5. So it's hundreds of thousands times our today's qubits better than when they just appeared. And that's a huge development, but we need more, okay, of course. And people investigate new materials for that, and new materials for new cavities, new qubits, new types of modes, different error correction techniques and protocols. A few words about this. So error correction, in a nutshell, okay, it's when you replace one physical qubit with a number of computational or logical qubits, or actually all the way around. When you replace logical qubits with a number of physical qubits, okay, so your system, so when you, for example, read like 50 qubit circuit, 50 qubit platform, most likely now it means that you need to multiply this number by something like 8 or something, depending on the type of error correction, because one logical qubit is created by a number of physical qubits. And why we need so? Because the system becomes more resistant to noise, to any errors, and so on. Yeah, so this is what's happening today in this area. Few conclusions. So today we discussed the superconducting quantum gates. They have a number of advantages. They have a number of disadvantages. In the end of the day, this type of qubits is the most popular. The vast majority of most powerful quantum computers today based on Josephson junction quantum circuits. This area grows a lot, and we for sure will have much more powerful computers very soon. The progress in this area is pretty fast. It's pretty fast. All right, so here is a slide about more read, and not only read but also watch. I put here a number of YouTube videos that I particularly like about the subject and about quantum computing in general. Also, I put a number of videos specifically by Sabrine Hasenfelder. She not only discusses process, but also like cons and critics in terms of regarding quantum computers. Okay, so I think one should also read and watch about the criticism. That's why I put these links here. I encourage you to read, to watch, and so on. And of course, you can also reach out to me if you have any questions. And I guess this one is the last yeah, this is the last slide. I just want to point out to this website, which is very useful, insightful, and so on. This is, in fact, the Quantum Consortium. It's a consortium of many labs and many vendors, companies, so on. It's called QED-C, Quantum Electrodynamic, or I mean, it stands for something else. I don't remember. It's QED-C, Consortium for Quantum Computing. And in this slide, if you navigate to quantum jobs over here, you will find a huge list of today's around 600 entries, which is update pretty much every day, like almost every day, with new positions in quantum, including the companies, business, and labs. And not only US, but also Europe, like Finland, Germany, Poland, Asia, and India, right? India. You see, India today. India invests a lot into quantum and growth, which is very good. US invests a lot. France, and so on. Yeah. So this is a very nice platform if you're interested in finding job in this area. This website is must to check. Okay, so it updates almost every day with new positions. Also, here on this website, you can find the quantum marketplace, which is pretty much the list of all essential vendors and companies for quantum. Okay, so you see the list is huge, and all these companies today develop quantum computers. Yeah, and it's impressive. It's impressive how much this area grows. Even Wells Fargo. Wells Fargo is committed to research and developing. Oh, that's very interesting. I didn't know they do so. Yeah, so you see, it's list is huge, and one can easily find a place to apply. Okay, so this is it. This is the end of today's lecture and the end of the course. Let me stop the recording, and then we can discuss if you have any questions.